Oh, I realized that I put the wrong link on the office hours. So anyway, I mean next Tuesday should be bookable, but somehow it was not bookable. Um, but anyway, I fixed it. So you should be able to book next Tuesday if you want to discuss your project. But if you don't, that's just fine.
And if project, again, the requirement is just the reading max.
Yeah, and process is optional, but of course, if you want to do a project with processing, it will be cool. Um, yeah, open-ended, and hopefully you explore something we didn't cover in class, of course. That would be fun. But if you also want to just try combining different stuff that we talk in class, that's also fine. So open-ended. Um, December 1st would be our last class. I will be traveling right after my class. I will be flying. Um, so that will be our last class. So present your project on that day. And the report, I mean, just write something about that. Will be due on December 15th. 2 weeks after, I mean, a week after the final exam. Right after the final exam, I mean. Cool. Um, So on Monday, we basically talk about, sampling and delay. So sampling is something that, we touch on, but we didn't really go deeper into it. But there's all sort of things you can do with, um, oops, wrong. How, oops, how do you status? Where I think I need to relaunch Max. Cool. So on Monday we talk about sampling, but basically, one of the interesting way to interact with sampling or play tilde is that you can actually use a line tilde to control it. So basically, this is sort of controlling like playing from 0 to 300 seconds within 300 seconds. So basically, what you are sending to this line is something like, this is the time and this is this number of sample index that you want to play. So if you play something from 0 to, 300 and you are playing 300 index, meaning that you are playing in the correct speed. And if you want to play it faster, then you want to play it, within 150 millisecond, but you play 300 samples of that. So, you can sort of like do stretching and, speed adjustment on that. But here we are basically just playing different chunk of that drum loop. Still coming out from my laptop. Let me see. This should work. So this is basically that drum loop thing, and we can play different part of that. Well, audition again. So this is the drum sounds. And we are basically just playing different chunk of that. So these are just different chunk of that. So from 16,000 sample to 1,700 samples, and you played it in 100 milliseconds. So you didn't order that sounds at all. You just play a different chunk of that. Um, so you can also build a, like a drum machine to that. But more interesting is that you can play all sort of different things using this groove thing. So, you know, you can play it. You can set loop 0. If you don't want it to loop, you could set loop 1 so that it will loop. And drum 2, meaning that the outputs will be stereo. So you get 2 of these outputs here. And the third one, I don't know what it is, loop sync output. So likely just let you know whether it's looping. And you will see these additional inputs where you can control which part of that you want to loop it. basically you just play those two parts. You could also set the speed by sending a signal into the first um, inlet. Cool. And we also talk about delay, and we will see a very interesting application to generate some string sounds today, like a synthesizer. So one thing we talk about is that this tap in, tap out thing. So basically, tap in is that you do grab some recording and then you delay it for 10 milliseconds and you play it back. So this is basically delay. So tap in 1,000, meaning that you take up every chunk of like 1 seconds as a whole, and then you reduce delay it. So this is sort of like the buffer size of your tape. Um, you can just use the default value, but here you can also set it to a certain amount. So we've seen some of these. Um, this is likely coming from this. So this. Okay, so now we are hearing these stuff. So you can play a song, the sound that you might be familiar with that we listened to again last week on Monday. But anyway, you can try, different. It's kind of hard to get a sense what's going on. But if you're using headphone, you will hear it basically increase the thickness and make it sound thicker or sound deeper with additional layer. So what's going on here is basically you have a sound and then you basically just delay it for 10 milliseconds. So it's a tiny amount of time that you couldn't really tell what's going on. But if it's larger, then you will hear. So if it's like 100 millisecond, then definitely you will hear that to attack here. But if it's like smaller number, then basically it blend together. So it just become a blended thicker sounds. That's my laptop sound artifact. So you can do all sort of things, you can also do your, so this is like easy ADC. So we talk about, this is DAC, so digital to audio converter. This is an easy ADC analog to digital converter. So you can also process that using your microphone to get the delay sound of your microphone. So something like this. So you hear your own self. So this is dry sound, wet sound. Anyway, and you can also create this echo effect that we look at last, on Monday, which is basically grabbing your voice and then bounce it back. So you see this feedback loop where you record it and you delay it for 5 milliseconds. And for 5 milliseconds, and then you reduce this uh magnitude by 0.8, 80%, and then you send it back to delay it again. So what you're getting is basically a decay version of your own sound. So your original sound will be something here, and then you times it with 0.8, and then so basically it's sort of like mimicking that in a space where you are shouting to a mountain, and the sound will just bounce back and forth, sort of like that echoing effect. So every time it bounces, it will decay, sort of like 0.8%, or you can think about it as like the bouncing ball effects, where that's homework 7 kind of actually. So you have droplet sounds, and it will sort of decay over time. And the last thing we talk about is this flanging effect. So flanger effects basically. So let's take a listen. We didn't actually look into it. So what's going on here is that now we can modulate everything. So this sort of the funny part of doing max MSP programming. But basically the idea is that, well, we have a sound, and then now we can do 20 millisecond. After that, we can also minus 20 millisecond to get earlier version of that. And now the idea is that, well, we have the sound, and we want to delay it, sometimes 20 milliseconds, or sometimes, we cannot go back in time. So what we can do is that this is like 40 millisecond. So can we just jump around these things? Sometimes 20 milliseconds, 30 millisecond, 40 millisecond, back to 30 millisecond, 20 millisecond. So doing a back and forth sound for that.
Sorry, my computer just stopped with that.
Yeah. So what we can see here is that if you do a number here, so let's look at what's the delay we are getting here. Cool. So you can see that this number basically just go from 20 to 40 back and forth. So it's a sine wave between 20, 40. So sometimes it's delayed for 20 milliseconds, sometimes it's 40 milliseconds, sometimes 20 milliseconds. So this will create this effect of flanging. So we can listen to it. I promise that I will find a better sounds, but well, I don't have it now. That's what we have. Um, let's figure out better sounds actually. Um, what else do we have? Um, do we have some other sound? Well, um, maybe we can grab one of these audio here. Let's see how this works. So we can have this, and let's remove these parts. So we can do the same thing with this. Oh, pretty nice. So what you're hearing now is that you have the original sounds and the delay version of that. So when I just so this is the original sound. Let's give it a listen. And okay, so this is the delay version of that. It's just a little bit wobbling because you are moving that sound sometimes 20 milliseconds later, sometimes 40 milliseconds. So it's like sort of like stretching a little bit. But what's interesting is when you combine these two sounds. If you listen to it, you will realize there are certain frequency that's gone, that's moving. So what's happening here is that there's like a destructive cancellation going on. So if you have a sound look like this, what if you basically move half of that frequency so that it basically do the opposite way? I'm drawing it very, very bad. So think about it this way is that, well, if this is like 20 millisecond and you have a waveform that has 20 millisecond wavelengths, then it will basically push towards at that stage where you will basically these two, when added together, it becomes like zero. So this corresponds to a certain, say, in 44.1 K hertz. This corresponds to a certain not 44.1 kilohertz. So if you have like 44100 samples per second, this corresponds to a certain frequency, right? So it will be, what frequency would that be? That frequency will be 44100 divided by 20 milliseconds, will be roughly 220.5. So this will be correspond to 220 hertz. So that meaning that, in this audio that you have, there's like so many different kinds of frequency. But when you delay it for 20 milliseconds, those frequency will be canceled out. So now you are doing this frequency cancellation. But what you are getting here is that the frequency will move around. So essentially what you're getting is a count filter where the frequency response looks something like this. So, well, not like this. So what you're getting with 20 millisecond is something like this is correspond to the frequency that you have. Everything that's the multiple of this frequency will be sort of like cancel out because that frequency will give you this, totally opposite waveform of your original sound, and it will cancel out. So what you are seeing is that this frequency will change over time, and that's why you hear that sound. That the frequency being extracted out from your audio is changing along the time. And the frequency, the corresponding frequency is actually determined by the millisecond samples that you are doing. So, these are some of the effects that you can do. Some of the flanger or chorus that we talk about are sort of similar. So chorus is where, you are grabbing this delay and then you just do it that way. So chorus will sort of like do this. And now flanging is about, when you move this delay around so that you are creating like a random frequency extraction that move around with a sinusoidal function. So that's why you listen to the audio, the sound, you will hear that, certain frequency will be extracted out. This is the original, and this is the mixed one. So you create that, halo effect where, certain frequency are being extracted, and that frequency will change over time. So this is flanger. And one thing that's very interesting that we can do with delay is we can actually create some interesting sounds. And this is known as the Kaplar's strong. Let me find the file. Where this file? Cool. So this is called the Kaplar's strong synthesizer, which is very simple, but it has very interesting sounds. So you can create sort of like string sounds just using a very simple delay and filter. That's all we need. So looking at this, what we are trying to do is that, to create this string sound kind of synthesizer. And the whole system is actually not too tricky. Is that, well, we have a random noise. And, this is our speaker. I don't know what speaker should be like. Let me just throw a speaker then. Oh, nice. So what you're seeing here is that you grab this audio and you go through a filter, a low pass filter, and then you decay it by a certain amount, say 0.9, and then you add it back. And this will create a loop actually. So this is not here. So what you want is that the thing will go through the effect and times 0.9, and then you add back to the original, and there's a delay. So that's essentially what we're seeing here. So you have a short impulse noise, and you want to send it to the speaker, but at the same time, you want to create this loop where you want to delay this noise and then filter by something and then decay its amplitude and add it back. And that's what we can get here. The theoretical understanding is a little bit tricky, but anyway, you can create some sounds like this. So let's do it this way. So as you can see, this is the noise, and then you have the line. So if I just get rid of these things and these things, so let's get started from scratch. So now we have a noise. So what you're hearing now is that we have this noise, and remember how we can do this. So this is the graph, the function thing. So what's going on here is that we are creating this envelope to modulate this noise. So the longer we have, here I already set the domain to 100. So when you are grabbing these points, you see that this is like 100 millisecond noise. And if I grab it into 10 millisecond, this is what it sounds like. Cool. So this noise is different from the pink noise that we have. So pink tilde, we get the pink noise. This is white noise. So what you're hearing here is the full spectrum white noise. But now we clip it with 10 seconds, and it will decay from 1 to 0 over time. So that's what we need. And now what we want to do is to have, let me save new so that I won't accidentally replace it. Cool. So what we want to do now is just use our tap in, tap out things that we have. So let's create a pair of tap in, tap out. What we can do is set this tap out to 10 milliseconds, and we will see how it sounds like. So now what you want to do is to grab these things and add it to that. So this is not fun. This is basically, having this and delay it by 10 milliseconds and add it back to the original one. So this is not what we want. What we want is potentially, we want to delay it for 10 milliseconds, and then we want to do a low pass filter. So here we can do this things called one pole object, and we can set a specific frequency, say 5,000. We can see how that change over time later. But this is essentially what we need already. So this filter, we want to actually times it by 0.9. And then we want to send it to our output here actually. And then the tricky part is that we want to have the 0.9 back to our original sound. Cool. So let's check this out. What's going on here is that you have the audio, you have the noise that you have. So we are actually doing that sounds already. So what you're seeing here is that the noise will be 10 millisecond short chunk of that noise. And then you will delay it by 10 millisecond. And that noise will be filtered by low pass filter. And then you will decay its volume. Otherwise, it will be an infinite loop. And then you send this thing back to the things and then to create it out. So what's going on here is actually, you can think about, you are basically creating different version of your original sound. So originally, you have a sound, and then you delay it by 10 milliseconds, and you filter it, and then you delay it by 10 milliseconds, and then you get this, and you get another version of that. And you want to sum all these up, and it will decay. So this is 1, this will be 0.9, 0.81, 0.729, blah, blah, blah. So you will have a smaller chunk of that. And what's your experience is that this actually create a very, very nice sound that has that harmonic frequency range. And that frequency actually corresponds to the time you delay it for. So we can try a different number here. So if we do 20, it becomes a lower sound. And if we try 5, it becomes a higher pitch. Cool. Shall we try this first? Let's try to do this, and then later we want to see how we can control the pitch of this. Cool. So this is the tap in, tap out that we talk about, about delaying. Cool. Shall we just try to do this? So first try to get these part done. These part, and forget about this loop for now. Let's do it. So do the left hand side first, and then do these to add it up. So, if we don't have these, it's just an impulse noise. It could be longer. But now if you add those back, then you can create it. This is called Kaplar's strong synth, one of the simplest synthesizer that can sort of create some string-like sounds. Um, I believe we've talked about everything in this patch other than this one pole thing. So this one pole is just a easier way to just create a low pass filter. So that one pole 5000 is actually a downgraded version of the biquad thing we talked about. So biquad, you have to determine a bunch of coefficient, but this is just like a quick shorthand for low pass filter. So it's sort of like a simplified version of the biquad things that we talk about. But this will basically create a 5000 hertz, low pass filter. And we can also try a different number for this, but it shouldn't affect too much on the outputs unless you do something small. So if it's this not large enough, it will be kind of flat. But it sounds like drums actually. Doing good.
Yeah.
Right. Doing good at homework.
Yeah. So hard, so I won't be using it on Monday, Tuesday.
Yeah.
So I won't be able to work on it. Yeah.
Oh, you mean physically?
No, like physically, I won't.
I mean, you could try to. You have a rebound?
Yeah, but you said to save it for the final, right? So I figured after this homework, I would install the refile.
Yeah, like it's 30 days. Yeah.
Oh, is it?
So you could start now. So yeah, it will cover until the report. But presentation is
Semester's almost over.
yeah.
Was, I'm already doing.
That's different projects. It's nice.
I don't know. Just, it's so much fun.
Ooh. Well, there's actually a better figure to show what this is in. So technically this is what I'm drawing here, even though it's kind of ugly. But basically you have a short noise burst, and then you want to delay it, and then you apply some low pass filter, and then you add it back, and then that's it. Like a super simple loop, but it can create very interesting string sounds. And the theory behind it is kind of similar to, chorus and flanging, where, by adding yourself with a delay version of yourself, the sound itself, you can sort of like do some cancellation on certain frequency or boost certain frequency, or, basically you are modulating your frequency over time. And that's essentially how this synthesizer sort of like create that frequency trend so that it create a nice harmonic sound. Um, are we good now? You succeed to get the tap in and tap out working. So this is only the first step. I mean, the ideas would be, well, this is just a single tone generator. But what if, you know, we can tell that the thing is actually doing something, right? This is actually changing the pitch somehow. So technically, this numbers actually correspond to, we could have it. I mean, if you want, we could try it now. So how can you turn the thing into this number? There's a connection between the frequency between frequency and this 12th number. So you can do some computation. It's actually quite simple to determine the specific sound. Good. Good. How do you mean that drop? Let's figure out what that is. I think it's a function. And the slogan won't be bigger, but we want to get that separate. One thing that might be tricky is the function should be the second outlet. This is one thing that always forgot. So you get the second output. That would be all the points where you can draw the line. So if I click it, you will see. So, start from 1 and go to 0 at, 10 milliseconds. And if you send that to this line function, it will create this shape, basically. Okay, cool. Now, how do we figure out how to do this? Any idea? How do we turn this MTOF to this? Turned out what we need is basically just let's just use 1,000, divide that. That's basically what we need. Any number divided by that. So let's try, expression 1,000 dot slash $1. So what we are doing here, $F1. Cool. So what we get is that, we have this 200, 220, and we want to divide it by 1,000. And let's see what the output will be. So, if it's like 220, then we get this 4.454 number. But basically, we can grab these to send it into our tap out. So now tap out, this delay will be determined by the frequency that you have. So that's essentially what we want. Let's try it. So now if it's just like 440, so now we basically get some pitch out for that. So what else you can do? This is like expression dot. One thing you could also do is something called this things. Whoops, what I'm doing. So alternatively, you can also do this. Cool. So these two are two different options. And now what we want to do is to trigger oops. We basically just grab this to our inputs, then we are done. Cool. Are you following what's going on now? So what I just added is just to turn some keyboard value into frequency. And now what we want is like 1000 divided by that frequency so that you get 5.7 or whatever. And that will be the millisecond of delay that we want. That corresponds to the sounds that you listen to, you heard. So, we try, tap out 10 and it corresponds to a certain frequency, tap out, 20 correspond to a certain frequency. And turns out their relationship is just modeled by that 1000 divided by frequency. So the desired delay, T delay here now is like just 1000 minus the frequency that you are interested in, that you want to generate. So now you can do expression 1000 dot slash $F1. We talk about this expression thing. Once you have $F1, basically the first inlet will become the float that you will put 174 here. So 1000 divided by 174, so you get 5.7. But on the other hand, if you don't like these things, you could also use this things called exclamation mark slash. So, there's like two different things here. If you do, divided by 1000, what you get is basically 174 divided by 1000. That's 0.17. So if you add an exclamation mark in front of that, now it becomes 1000 divide. So your number divided, use 1000 to divide over 174 so that you will get the desired. It's cool. So you can play with different numbers here. These are the delay. These are the frequency. So you see that when you have a longer sound, it doesn't quite work. It become very messy. But you have a short impulse, then you can hear that nice sound. Are we good now? Are you getting some sounds? Very simple pitch. So yeah, this sounds like string, hopefully, if you are persuaded. But it's sort of like one of the simplest form of string synthesizer, which is like very simple, as you can see. This is the block diagram. And Cool. Cool. I guess we can move on to look at the last module of the course. We talk a little bit about recording, right? On Monday, but basically, you can use a microphone, of course, to see what I'm talking. So here you see the sounds. I can play it back. So you have the microphone inputs, but you can also just route directly your microphone outputs all the way to again and then get the outputs. So if I select to route it, then you will hear my voice right away. But anyway, this is also, my real-time sound that you can see what's going on. So, these are different ways of doing it. So recording, we talk a little bit about it. We talk about this very fancy, sort of like recording thing where basically you want to select one. So when I toggle it, we will get a one, and then you will delay this message to 2 seconds, and then you will trigger the zero, and this zero will turn it off. So this sort of like a countdown, basically countdown. So it will be one, and then after 2 seconds, it will automatically turn it off. So this is a tiny, counter or countdown for you to control the recording interface. And if you want to do record, basically it's just record tilde and rec, then this sort of like buffer kind of similar. So you first have to create this buffer so that you create so what you can sort of like place a analogy to other programming languages is sort of like at the top is like buffer. So you want to say buffer rec equal like a new, I don't know, waveform 2000 length. So you create something new that is not initialized here. And now record tilde rec is that now you want to um, specify what this number is. So rec equal to your input from mic. So this is just like writing a program in other programming language, just that now you first initialize it and you define the value here. Once you record it, now this buffer thing is still a variable, kind of. So you can think about buffer tilde is just a variable. So this rec will be 2 second variable that can store anything. And if you want to record it, then it will override whatever that you have in record. So now I can record a different sounds. So, and how you interact with this recording is that you can basically just, you can play it. So now I can record. That's, the recording. So you can do everything you want to do with play. So, the thing we talk about, back and forth, you can reverse it. You can do all sort of like different variation of playback. So, in this case, we can record something and, you can play it back in different shape. Somehow. We can record something. And now the thing we talk about, like if you play it like 0 to 2000, but you played it with 4000 millisecond, meaning that you're stretching your audio. So it sounds lower pitch. This is a stretching, and you can play it faster. We can record something. And you can also play it reverse. So now you can basically create like a scratching idea on top of that. And there's all sort of things you can do in Max. So panning, which is likely kind of straightforward to you, is that basically you just want to pan between these two speakers, basically. So what we can do, oops, what's going on? Okay, so if we have like a 440 sound, and we can pan to different speakers. So you can see that, the output is like everything at the left speaker, in the middle, at the right speaker. So that's what you're seeing here. So basically, you have the sounds here coming in, and you want to type this to different gain based on some calculation here. So these things are basically just doing what we are doing. So this is like 127 and divided by 127. So you will see this number here. So now when I click in the middle, it will be 0.5-ish. So the output will be 0.5, and the other one will be just 1 minus that. So the reason why we need this line function is so that you create a smooth transition between those two numbers. So let's see. So let's play.
With a party at, I need some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium.
So I can move it to the left channel, the right channel, and if I move it to the middle channel. So this line basically will sort of, oh, this is like 0.5. And so what if I do it with 1,000? Then what you're seeing
with a party at, I need some of that primitive action.
Is that it will slowly go to one, so that it won't be, there won't be the click when you are, rapidly changing the pen. So what you're seeing before is like 20, so that you create that smooth transition between this number from 0 to 0.5 to 1 smoothly. So that's what we can do with this line thing. So basically it's like how long should we go to the next number? So this $1 is our target number, and how long you should spend toward that. So 20 milliseconds is like, very short, but it still prevent, Max from producing something really sharp. That's because you want to quickly switch a sound to another channel. So usually if you want to make a smooth transition, you want to add like, 20 milliseconds so that it slowly fade through with that. So this is like linear crossfade. One thing you might notice is that, I don't know if you can hear it. I mean, the sounds should sound slightly lower volume in the middle. And that's because this linear crossfade doesn't really work in keeping the sound with the same volume. So here is a figure of what's going on with that. So when you are grabbing the gain, so gain is like you have the so you have the signal. So you have a signal, and if you time 0.5, then you become, smaller in its magnitude, right? However, the energy or the perceptual understanding of loudness is actually not linear. It actually corresponds to the magnitude, the square of that magnitude. So what you're seeing here is that, this is like 1. At the left, you're seeing is 1 square plus 0 square. And then at the right is like 0 square plus 1 square. So these has the energy, total energy of 1. But in the middle, what you're seeing is that both become 0.5. However, the energy now is 0.5 square, and this is 0.5 square. And what you are getting is basically, only 0.5. So that's something we know about, this linear crossfade, is that if you just linearly change the gain, as we are seeing here, it will create a dip in the middle of your position. So when you have it in the middle, it's the energy actually become half only. I don't know if you can feel that, but this is louder than this.
Give me that kick drum, keep me loose like Valium. If you with a party at, I need some of that primitive action. Give me that bass, give me that kick drum, keep me loose like Valium.
I mean, it's only a half energy difference. So our listening perceptual is actually logarithm, so it's not a huge difference. But to solve that, there is actually some way to do it. So the idea is that then what would be these numbers so that it sums to one? So the idea would be something that, so this x squared will be 0.5. So what we want is basically, square root 0.5. So that you get 0.5 here, and you get 0.5 here, so that you get everything. And square root 0.5, basically that's, square root 2 over 2, that's basically 0.707. Ish. So 0.7-ish. So you can see here 0.707. That's essentially what we want to have that equal power crossfade, basically.
Some of that primitive.
So what we can see
With
here,
a party at, I need some.
and in this
Some of
case,
that
basically
primitive
when you
action.
are
Give me that
running
bass, give me
around
that kick
that,
drum. Keep me loose like
you will keep
Valium.
the same
With a party at, I need
energy.
some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium. If you with a party at, I
And the difference here,
with a party at, I need some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium. If you with a party at, I need some of that.
so there's obviously some diff in that one. So it's not so clear which one is better, because this is also not the end of the story. But you can definitely see that, equal power crossfade are adding additional boosts in the center. So that's essentially what we call equal power crossfade. What we are seeing here is the formula of doing that, but formula is formula. But essentially what you want to do is to keep the total energy between two channels as one as possible. So, this will be 0.5 square, 0.5 square, but at some point here, and the function is something like sine 2 pi times p square. So basically what that value will be is a sine function, and this is a cosine function scaled by something. But anyway, the goal is that you have this scan pattern. It's like curve a little bit upward, and this one is a little bit outward. But anyway, you keep the power as the same across the panning ratio. So panning is about, how do you go from like a mono sound and you want to move from this channel to that channel. And you can think about, in the stereo, spatial, stereo, and then now you are thinking about the spatial placement in this room. Then how do you move that sound source around your space without feeling that sounds becomes fainter or quieter? But how can you keep that equal power? So this is sort of like trying to mimic that behavior where the sounds will have the same power. Of course, this is not the end story. So there's actually another things where, we haven't, think about where the human is standing at. So this is the final chunk of that. So, this is essentially what's happening. So if you have like two speakers, and while I'm standing here and while I'm standing, is it making some sound? Okay. So what you can do here is that, your listener could be standing at different places. And what you want to do is that you want to create that, I guess, let me explain it this way. So the difference between this equal power thing is that equal power meaning that you are of the same distance to that sound source, right? So what happened in this equal crossfade thing is that, well, you have your first speaker here, and you have another speaker here, and I'm listening here. Maybe I will move it closer so that you feel the difference. So what you're listening to is that, well, when we pan to the left, this is the distance. and we feel that energy. And the energy of a sound wave is like the energy of a sound wave sort of like will decrease in proportionally to the square of the distance. And so now you want to pan to the other side, it's also distance d. So what we are doing with equal power crossfade is actually having, say I have a sound object, say a dog barking. So I don't know, I have a dog here and I have a dog here. So what the dog perceptually is actually moving on this plane where the distance is the same. So this is create a very interesting thing. It's about, thinking about where that object is going. It's actually going inside the wall. So that's also not something we want if you want to have a realness. If you're aiming for a real feeling of that, when you're standing here, when the object go from that speaker to this speaker, in the middle, it's actually closer to you. So it should sound louder. So the next part of that is just about, can we sort of mimic that behavior? So I want to see a sound going from this speaker to the middle of these two speakers all the way to that speaker. But the question is that when we are in the middle, it's actually closer to the listener. So in this part is just doing a bunch of computation. It doesn't have to be in Max anyway. But you can also just try to do that. So this is the equal distance case where the object is actually not moving from this to that in a linear way. It's actually going into the wall because you are at some position. So we can listen to some of the panning situation where you can set the speaker angle and the speaker distance. So speaker angle basically is that how wide this thing is. So a smaller angle, then this thing is roughly the same. But if this speaker angle is very large, then this lens and this lens is quite different. So if you are standing so close to these speakers, now if an object moves toward in front of you, it sounds very loud, much louder than it's in the opposite way. So we can get a lesson of that.
With a party at, I need some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium. If you with a party at, I need some of that primitive action.
So what we can show is that if we have a very large speaker angle, I think speaker angle is, let me try, 80 maybe 75 is the largest. Cool. Let's try it this way.
With a party at, I need some. With a party at, I need some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium. If you with a party at, I need some.
Well, I think there's something wrong here. I'm not quite sure what this speaker angle is.
With a party at, I need some of that primitive action. Give me that bass, give me that kick drum. Keep me loose like Valium. If you with a party at, I need some of that primitive action. Give me that bass, give me that kick drum.
But anyway, this speaker angle just determine how far away you are from that. And all these computation, as you can see, is just calculating how far away you are from that speaker. And you have to do some calculation to determine, what if, the sound, what you want to compute is that when the sound is here, how far away you are from that. And you want to apply these things to determine the gain between left and right channel. So that's everything going on here. Tons of computation, but you can see, we don't need to look into it, but you can see some of these things are basically just using expressions. So you can see how Max can be doing all sort of computation, expressions, square root, $f1, $f1. So this is $f1 square plus 1. And here you can combine different numbers to compute what you want. Cool. So that's panning. So panning is about, having a mono source and you want to move it around your speakers. So that's different from balancing. So balancing is when we have a, stereo inputs. Cool. Let's look at this. Okay, the good old sounds. So what we are seeing here is, this is basically, I don't know what's going on here. Let me just check this out. So what we want to do here is that we want to sort of like split the sounds into stereo. I think we could just look at this. Let me see this. Kind of forgot what we are doing. Oh, okay, it's working now. So now you can get, this is the left-hand side. This is the right-hand side. So, you can pan it through the left and to the right. This is essentially what we know, right? So what we can do is this blending things is that now can we sort of like mix them together to also send something from the left channel to the right channel and send something from the right channel to the left channel. So what's going on here is that it's actually creating that effects that's doing some stereo mixing. Let me see if I can find a now we finally got it. So what we are seeing here is that we are grabbing a stereo sound. And what we are gonna do is that, even we have a stereo sounds, we can actually create how wide it is by, modifying it. So we have like L channel, we have R channel. What we can do is just combine these two, and then we will get the mono channel, which will refer to a center channel. So here I'm just showing you how you can sort of like remix of these two sounds to create that, do you want to do mono or stereo? So if we have 0, then you can look at this ratio. So we are doing some mixing here. But anyway, the output will be 1 for the mono and 0 for the stereo. So this is basically, having a song, but we sort of like just add them together and then create a mono version of that. And if we are doing 1 here, then basically this is the original sound. So what's going on here is basically you can play with this is that, well, can we sort of like blend between mono and stereo? So this idea is that can we get, say, 50% of this mono inputs plus original 50% of the original right channel, 50% of the mono version of that, plus the 50% of original left channel. So here, the blending idea is that can you sort of like create that space? So let's give it a listen. This is the monophonic version of that. This is the original stereo version of that. You should be able to hear that it's wider than the mono case. This is the original stereo. we're playing with that spatial wideness of that. And this idea can actually be extended to just this the mid-side mixing, and that's essentially what I'm talking about here. So the idea is that you create two channel here. So one of that is like this is the mono. So you have left and right channel. And so now this M equal to L plus R minus divided by 2. So this is sort of like the mono version of your signal. And the side channel is the difference between your left and right. So side channel will be L minus R divided by 2. So what we'll see here is that now if you do M plus S, then you basically cancel out these two R. So M plus S is L and M minus S would be R. So this allows us to, sort of just playing with the ratio between these two things to get, how many L and R to leak toward that. So that's we will grab this stereo thing. Cool. Let's play it. So now this is the same little idea. Now without any side amount, these two basically count to both of them become the mono version of that. And so when I add more side amounts to that, and if I add channels. So this is called like mid-side mixing. So basically you divide the sounds into the mono, the middle channel of that. And the difference between your left and right channel is the side amount. And you can play with the the ratio between M and S so that you create the wideness of the sounds that you have. And of course, this is just like stereo and think about these surrounded speaker. So that's all about, all the spatial audio. How do you place the sounds? And if your sound is stereo or you have multiple microphone recording your sound source, then how do you make these sound source move around in all the speakers while keeping the desired, perception of how far away that sound is. And you want to have a very precise localization of the sounds that's coming from a certain direction. And that's what all these spatial audio is about. And here is just an example showing you that, by even getting one stereo sound, you can actually manually create its mono version by just adding them up and get the average. And by playing with the amounts of the average with the difference between these two channels, you can actually widen it to the original stereo sounds or, collapse it into a mono version. You can even expand beyond that. If you do sine amount larger than 1, you can actually expand it even further. But you will create some distortion. Cool. So I guess that's sort of wrap up what we want to cover in Max. Of course, there's so many other things that we can do in Max. I will likely show you something next Monday on some of the case studies to see what are some real life application of Max MSP. But we are basically scratching the surface of what Max MSP can do, and of course there's tons of things that going beyond this. And as you know, Max MSP has a huge, very steep learning curve. But past that, then if you want to extend to some other interesting project, and now you have additional tool that you can use that's different from other programming language you might know about. And this is like a very unique programming language that's like signal-based, real-time focus. Cool. And when's homeworks due? Due Monday? Okay, cool. Good
I
luck.
also saw the project pitch was due Monday. We submit for that.
You mean project pitch? I don't think we have project pitch
I
anymore.
saw it in grades. Yeah,
Ah, okay. I will remove that.
okay.
Sorry for confusing. So we won't do a project pitch, just do whatever you like. Yeah, just don't do something too trivial. I guess that's the only pitfall. But feel free to explore whatever you like.